Hello everyone, and this is going to be question number 5 from the 2025 AP Calculus BC exam. This is a differential equation question, but you will notice that there's a couple sneaky things thrown in here. In particular, a Taylor polynomial, which we've just covered. All right, so we have a y equals f of x, and we have a differential equation. It's a little cut off there, but it's 3 minus x times y squared with the initial condition of f of 1 equals negative 1. All right, part A is asking us to simply find the second derivative, evaluate it at 1, and we're going to go ahead and plug that in and evaluate. So here we go. First things first, I need to take that differential equation we were given and apply the product rule here. So 3 minus x times the derivative of y squared, which is 2y. By putting that dy dx right there, you would actually earn what's called your chain rule point. So you'll notice here, point 1 is simply doing the product rule correctly. Point 2 is making sure you don't forget that dy dx here. Plus, and then your right term, which is y squared, times derivative of 3 minus x is negative 1. From here, you now simply just have to plug in x as 1 and y as negative 1. So I plug all of these things in. Now I do want to note here that this value right here that I've highlighted, actually the dy dx value. So I went ahead and did a little side quest over here and actually evaluated what dy dx was at 1, negative 1, and got that equal to 2. This is actually going to be important because we're going to need to use this a couple times throughout the problem. So we'll talk about that in just a moment. As you're seeing with a lot of these non-calculator problems, as soon as you get some sort of numeric calculation for the problem, you stop right here. What I have boxed in on screen is what I would totally say is your final answer. However, in case you went ahead and did the computations, the answer does end up being negative 9 here. And so just to confirm over here, here is the score of how the 3 points are earned. You will see again anything of these forms work. And then there is a lot of scoring notes here. A lot of scoring notes. This might be one of those questions that if you do have questions about how you might earn some partial credit for this, be sure to just talk to me and I'll look at it and I can decipher these scoring notes a little bit better than probably all of the information that's provided here. But that's really to explain that there's a lot of different ways to answer this question that you can still get to the same result. Okay, part B. It is time to use the second degree, oops, that is not what I wanted to do, the second degree Taylor polynomial of f for about x equals 1. So we're centering this at x equals 1. So let's go ahead and let's build it out. So here is that polynomial. So it would be f of 1 plus f prime of 1 times, since it's centered at 1, x minus 1. That right there is essentially the equation of a line. And then you have to apply that second degree as well. So f double prime of 1 x minus 1 squared over 2 factorial. Now, these first two terms, the linear part of this, you get by just taking the f of 1, which was given to us, f prime of 1, which we had found back up here in part A. So I told you we were going to be using that again. So that's going to be right there, x minus 1. And then the second derivative, well, we had just found that back in part A, so that is just me inserting it right there. Now, this is one of those classic transfers, so that if you actually got the wrong answer for A, but you transferred it appropriately here to B, so whatever number you got here, you have to apply it down here, that's going to be all right. Now, would that mean that you can put this entire crazy thing there instead? Well, the answer is technically yes. With that being said, you will note that it's a lot cleaner to look at this answer this way. But in theory, if you actually copied all that, again, there's lots of you see my work. I just did a bunch of 2 times 2, negative 1s and 2s. So it was solvable. It was simplifiable, if that's even a word, to be able to get that answer. So you'll see the first two terms earns 0.3, and then the final term earns the fourth point. All right, then we move to part C, which is another topic from Unit 10, which is the second degree is used to approximate 1.1. We want to, as soon as you see this right here, as soon as I see that, I'm thinking, oh, there it is. There's our keyword. We're going to be using the Lagrange error bound. Now, we've been talking about this in class a lot, and there's really not a lot of work you actually have to show here, okay? So whatever you write here, r of 2, f of x minus p sub 2 of 1.1, or just simply the word error, as long as you say it is less than or equal to, and then you create the next term. So since it was a second degree, we're using a third degree. That 60 was handed to us right here. It said that the maximum value of the third derivative was 60. So I plugged that 60 in over 3 factorial times this. Now, you could technically stop right here, okay? And I'm going to go over and show you that if you go over here and you just simply write this answer right there, that you are going to be fine, okay? And you can actually say 0.6 is earned from presenting either this notation or that. And you can tell I would prefer this for sure. That's a lot easier to work. And then to earn 0.7, you first off had to have gotten this, but then you have to explicitly connect the error bound with 0.01, just simply communicating that the error is less than or equal to 0.1. Now, it actually is equal to 0.1, but when you say less than or equal, you're going to be essentially covering your bases here, and you are going to be good. But make sure the most important thing that you do is do not say that the error is equal to. This is an error bound, so it is at most going to be this value. It is not going to be equal to exactly that value. Okay, final part is part D, and this is a topic from Unit 7. This is one of our asynchronous lessons, at least if you're watching this in 2026. The Euler's method process to be able to approximate 1.4. Now, Euler's method, I personally like to set it up as a table here. So we started with the point 1, negative 1. You evaluate dy dx at 1, negative 1, so we get 2 as our answer. And then to figure out your change in y, so about how much y is changing, you have to take your delta x, which in this case was 0.2. It is 0.2 because they said to create Euler's method with 2 equal steps. So we want to get to 1.4, so that's why 1.2 and then 1 are my steps. So that's my delta x, and then again the dy dx, which we had just found over here as 0.4. That gets added to the y value to give me now the negative 0.6, and if you got that far, you got 0.8 for this question. And then we repeat the process one final time. You find dy dx by plugging in 1.2 and negative 0.6, and you can see that I wrote my answer as an unsimplified answer because I did not want to multiply those things together. And then finally, to get my delta x, we took the negative 0.6, which was the y value. I added the delta x times dy dx, and so this large term right here is actually the y value. And if we actually go over to the scoring rubric, if you had actually done all those calculations, you would have gotten negative 0.4704. I do not think you would get that on a non-calculator on your own, nor would I recommend it. So in that situation, I simply just wrote this as my final answer, which earns me point number 9. And here is the scoring notes in case you want to take a look. And there is a much more organized table if that helps for you as well when checking over your work. That'll be it for 2025, number 5.